The Sun, the closest star to Earth, has a radius of about 700,000 kilometers and a mass roughly 330,000 times that of Earth. Because of this immense scale, it is extraordinarily difficult for us to grasp its size through everyday human senses. Structurally, the Sun is divided into the core, the radiative zone, and the convective zone. The convective zone alone is as thick as about 16 Earths stacked end to end. Every second, the Sun converts around 5 million tons of hydrogen via nuclear fusion, functioning as a colossal reactor that has illuminated the solar system and sustained life on Earth. This activity has continued for about 5 billion years. Of course, this glow is not eternal. The Sun has a finite lifetime. So, when will the Sun reach the end of its life? And after the Sun dies, what happens to Earth? In this episode, we explore the Sun's final stages and the future of the solar system. The Sun's energy comes from nuclear fusion in its core. There, temperatures and pressures are extremely high, and hydrogen nuclei, protons, move at great speeds, repeatedly colliding and fusing to form new nuclei. Through a chain of fusion and decay reactions, hydrogen is ultimately transformed into helium, and the enormous energy released in the process is what enables the Sun to shine. However, hydrogen is not infinite. In about 5 billion years, the hydrogen in the Sun's core will begin to run out. At that point, the Sun will no longer have enough energy to push its outer layers outward against gravity, and the core will begin to contract under its own weight, gravitational contraction. Although the core's hydrogen is depleted, hydrogen remains in the outer layers. As these outer layers contract, nuclei collide more frequently and fusion becomes active in the outer shells. Even though core hydrogen burning has ended, the helium-driven gravitational contraction and shell fusion energy will push the outer layers outward, causing the Sun to expand dramatically. In this phase, the Sun becomes a red giant. When that happens, the Sun's outer envelope is expected to expand to about 150 times its current size, and Mercury and Venus will be completely engulfed by the red giant Sun. But what about Earth? The radius of Earth's orbit is about 150 million kilometers. If the Sun expands to around 150 times its present size, it will reach approximately Earth's orbital distance. For a long time, this led to the assumption that Earth would also be engulfed. More recent calculations, however, suggest that during the early red giant phase, the Sun will undergo significant mass loss, which reduces the Sun's gravitational pull. As a result, the orbits of Earth and the outer planets expand outward, orbital migration, making it increasingly likely that Earth will not be swallowed. Even so, Mercury and Venus are expected to be consumed. That said, even if Earth is not engulfed, the Sun-Earth distance will change profoundly. Consequently, most of Earth's atmosphere will dissipate into space, and a global ocean of lava is expected to spread across the surface. Surface temperatures would exceed 1,000 degrees Celsius, rendering the planet utterly uninhabitable for life as we know it. In the outer system, surface temperatures would also rise, and some moons of Jupiter and Saturn might briefly approach conditions favorable for life. For example, Europa's thick ice could melt, potentially becoming a world with oceans more akin to Earth's. Even so, there would not be enough time for life to evolve into intelligent beings like humans. The reason is that on Earth, it took about 4 billion years for the earliest life to evolve into humans. Under the hundreds of millions of years timescale of red giant evolution, there simply isn't enough time for complex evolutionary paths to play out. After the red giant phase, fusion continues in different shells, but the core eventually uses up nearly all its hydrogen, leaving a large mass of helium. The core contracts again, while the Sun's outer layers are expelled as a planetary nebula, and the Sun becomes a white dwarf. As a white dwarf, its diameter shrinks to roughly Earth's size, or slightly larger, becoming extraordinarily dense. In the core's earlier phase, helium fusion formed carbon, but once the Sun becomes a white dwarf, there is essentially no ongoing fusion to provide new energy. The surface temperature gradually drops, and the star slowly cools. Earth, having become a hellish inferno, will eventually become a bare rocky planet, orbiting the remnant of the Sun for a very long time. Over trillions of years, the white dwarf Sun will exhaust its residual thermal energy, losing the ability to emit visible light. Eventually, the Sun will no longer be visible to the naked eye. By then, the geothermal heat of the outer moons, around Jupiter and Saturn, will have vanished, so even if life had emerged, it would safely go extinct. After about 100 quintillion years, the white dwarf cools to the point where it emits virtually no electromagnetic radiation, reaching the state of a black dwarf. The planets of the solar system, including Earth, will orbit in near total darkness, circling the black dwarf Sun, illuminated only faintly by distant starlight, if at all. And around 10 to 20 years later, the black dwarf and its planets will have emitted gravitational waves for immense spans of time, leading to orbital decay. They will gradually spiral inward and ultimately collide and disappear into one. The result would be a pitch-black object, roughly Earth-sized, formed from the Sun and all the remaining planets, drifting through interstellar space, the final portrait of the solar system. Of course, this scenario assumes that over 120 billion years, the black dwarf Sun never collides with other objects and never interacts strongly with external planetary systems. In reality, stellar encounters and galactic evolution likely make the long-term outcome more complex and uncertain. In any case, human lifespans are on the order of 100 years. We don't need to worry about 10 to 20 years, or even 5 billion years from now. Cosmic timescales far exceed the scale of human life, and our concerns are dwarfed by the grandeur of astronomical time. That's all for Curiosity Science. See you next time.